Right, so P is 30 pounds. And one more important piece of information that we do need. But yeah, the diagram, and then one more piece. Right, so we need that information because, again, it doesn't, unless it says it's an equilibrium or we know it's an equilibrium problem, that's not going to be true. But in this case, they tell us we're designing this in such a way so that this will be the case. So we need to find what value of F makes this true, that the sum of moments around A is going to be 0. All right, so we can make our diagram for this. Again, not a free body diagram, but it still is going to help us get our equations out of here. So we have the A at the bottom. So we're applying that force of 30 pounds at the top of it. I'll call this point, I guess I already named those points there, D. Now, other force, we don't know its magnitude, but we do know that it adheres to a 3, 4, 5 triangle, so we know its direction. And I'll name this E just for convenience. And then we know this is 12 foot and this is 6 foot. So no magnitude, known direction on this one. For F, it's an unknown magnitude but a known direction. And now what we didn't see before when we were dealing with particles is now the length of this object. So the object we're looking at here is this entire pole. So we're not concentrating it down to that single point, but the dimensions of it will now matter for solving the rest of this problem. All right, so we have a little bit of time left. So let's actually get to the equation step here. So what equation will we use for this problem? Right, since that's what we're looking for, we can say we want to find the sum of moments around A, and we're told from the given that it's going to be equal to 0. So what we need to find here, again, we can't assume that unless it says it's in equilibrium, or in this case it was given to us. We need to find the right-hand side for this problem. So we're presented with a similar situation that we had in the last one. We have these forces going off in non-XY directions. We do want a coordinate system here. So we could find, since we want the moments around A, the distance between A and then the perpendicular to that line of action. But again, that's going to be tough to do. So an easier way to do it is, instead of finding that, breaking them down into horizontal, vertical components and analyzing it that way. So this vector is going to be some of it going to the left and some of it going down. But both of those are acting at D. And then F, some of it is going to the right, and some of it is going down. But both of those vectors act at E. So if we're summing the moments here, so let's take it one piece at a time. So what is the value of this force, not necessarily as a decimal, but what's this force going to be equal to? Right, so that's the force. So I'm talking about, I'll call this Px and Py, and I'll call this Fx, Fy. So remember, a moment is a force times a distance. So what is the distance, the perpendicular distance between Px and A? Right, so it's 12 plus 6, so that is 18 from A. This is in feet. And this was in pounds. And then does this Px force positive or negative moment around A? Right, it's positive, so again, holding at A, pushing in this direction, it's creating a counterclockwise moment around A. I will include positive there just so we remember that we actually did check and it was positive. We broke this into that second force, Py, So Py is going to have a value of 30 sine 45. What is Py's perpendicular distance to A? Right, so this has its line of action, passes through that point A. So that distance, it lies on that, the line of action passes through A. In that case, the perpendicular distance is always 0. It does not contribute to the moment about it. So this whole piece goes to 0. Now for the fx component, what is fx equal to? Right, so we don't know its magnitude, but we know it's a piece of f, and we know specifically, since we know the direction, 4/5 times f, and then the perpendicular distance from fx to A. Right, so these forces are acting at E, they're closer to A, so that moment arm, we call it, is smaller, 12 feet, as opposed to 18 for the previous one. And is fx positive or negative around A? Right, negative. And then just so we have everything here, we'll have 3/5 f, and we can see that fy also has its line of action pass through A, so it also has 0 as its moment arm. So this term also goes to 0. So if we look at our sum of moments, the only thing we don't know here is f. So we have one equation for that one unknown. So the f that makes this in equilibrium, so it's not tilting to one side or the other, solving for f, we get 39.8 pounds.